So here we'll check out part C of number 2 from the 2013 BC exam. And we have this polar graph, and in part B it described a particle that was traveling around this polar graph, the limacone that's graphed here, and the equation of that limacone's right here. And they did tell us in part B that the relationship between theta and t was that theta was going to be equivalent to t squared. Now in part C they want us to reconsider that particle and find a position vector in terms of t. Well, what we can say about the relationship between x and y with r and theta is that x is going to be defined to be our cosine of theta at any point on a polar curve, and y is going to be defined to be our sine of theta at any point on a polar curve. If you check out the beginning of part B, we actually did a little derivation for this formula, and then this one is found in a similar fashion, but this is probably stuff that you pretty much have memorized if you've worked with polar equations enough. What we want to do here is we want to try to make these formulas x of t and y of t. So if we can do that, we're going to have a position vector before too long, an x component of position and a y component of position. So let's just try to manipulate these a little bit. What we can say right away, and I'm actually going to get these out of the way, I shouldn't have put those there, I'm going to need that space to do a little bit of work. So what we can say about x is that x of theta is equivalent to, so I'm writing x as a function of theta. If x is equal to r cosine of theta and r is equal to this, what I can go ahead and do is I can put 4 minus 2 sine of theta in place of r right here. And so x of theta, x as a function of theta, would be this. We actually did do that in part B. I don't know where that extra grouping symbol came from, so we'll get it out of the way. And then if we want to do a similar thing to write out a formula for y as a function of theta, all we're going to have to do is replace this r with what r equals. So 4 minus 2 sine of theta replaces the r here, and then times sine of theta. So it's easy to write x as a function of theta and the y coordinate as a function of theta, but what we want is we want a position vector in terms of t. So what we really want is we want a formula for x of t and we want a formula for y of t. And if we're writing this as a vector, what we typically do in math is we list our vectors almost as their ordered pairs with these symbols denoting that they're vectors and not ordered pairs. So I want a formula for x of t right here and a formula for y of t right here. Well, this is pretty easy to do because they tell you that theta is equal to t squared. So all you have to do, if you have this formula for x of theta, put t squared in place of the thetas, and you have your formula for the position dependent on t. So I'm just going to copy this, our formula for x of theta, into this position, but I am going to put t squared in place of all my thetas. So I'm looking at 4 minus 2 sine of t squared, and then that's going to be multiplied by cosine not of theta but of t squared. And I'm going to do something similar for y of t. I'm just going to take my expression for y of theta and I'm going to replace the thetas with t squared so that that formula depends on t rather than theta. So I'm looking at 4 minus 2 sine of t squared times times sine for y, right, sine of t squared. So this will be your position vector at a non-specific value of t. If you wanted the position of the object at, say, t equals 2, you could put 2 in place of all the t's and evaluate, and you'd have the position of the object along that limacone at that time. Now, it doesn't ask us to do that, but it does ask us to find the velocity vector at time t equals 1.5. So if this is our position vector right here, so we'll label that and just kind of box that up since that's part of our answer. And, well, I apparently did this on a little bit of a slant. Let me try that one more time across the bottom so it doesn't look so goofy. So here's our position vector. And what we want to do for the second piece of part C here is we want to find the velocity vector at time t equals 1.5. So our velocity vector at 1.5, since velocity is the derivative of position, all we need to do to find the x component of velocity at 1.5 is we need to take x prime of 1.5, and that's the x component of velocity, and then we need to take y prime of 1.5, and that's the y component of velocity. Now in math and AP calculus, when we specify a vector, we're typically not going to resolve it and find its magnitude. Now if you wanted the speed of the particle at t equals 1.5, once you have these two components, you'd want to draw your vectors and resolve them and do a little Pythagorean theorem finding the magnitude of that resultant vector to specify the speed. But if all you want is the velocity vector, listing it like this is going to be good enough. I'm going to do a little bit of work on the calculator here, and we'll come back and talk about the conclusion. So I guess I got a little quick there whenever I paused the video and went to the calculator. The direct way to do this, to find x prime of 1.5, is to take the derivative of this using product rules and chain rules and then evaluate it at 1.5. But since the calculator is in play, use that to your advantage. We just need to know the derivative at a point. We don't need the velocity vector at any time t. If we did need that, we'd have to take the derivative of this formula that's written out right here using product rules and chain rules, and that'd take a little bit of time, but it's not too bad as long as you're careful. But if the calculator's in play and you just need to evaluate that derivative at a single point, the work that I have over here on the calculator will do that. So I grabbed the numerical derivative option out of the math menu of the TI-83. I typed in the function that I wanted to take the derivative of, and so I typed in this function. I next had to specify the variable of differentiation, which I typed x into the calculator, so that's why you see x's here and not t's. And then I had to give it another comma and tell it the value that I wanted to evaluate the derivative at. And so I get my x component of velocity to be negative 8.072, rounded or truncated to 3 decimals. And I didn't do the y component yet. If I have this in there already, I can use the second entry trick to make that same expression reappear. This expression for y is pretty much the same. The y coordinate of the object is pretty much the same, except we have sine at the end here instead of cosine. So I'm just going to go back and overwrite that cosine with sine. I'm still taking the derivative with respect to the variable I typed into the calculator, which is x. Still evaluating at 1.5. So my y component of velocity is negative 1.72 if you truncate it, or excuse me, 1.672 if you truncate it, negative 1.673 if you round it to 3 digits. And like I said a few minutes back, if you're just looking for the velocity vector, this is good enough. There's no need to resolve this vector, no need to draw a vector of magnitude negative 8 in the x direction, and then a vector of magnitude negative 1.6 in the y direction, and find the magnitude of this resultant vector. If you wanted the speed at 1.5, you would have to do that, but if all you're asked for is a vector in calculus, this is going to suffice.